Hey guys, welcome back to another video. So let me first check. Uh, am I audible? Let's see. Am I audible? Yeah, let's see. So we are s- studying phase controlled converters. What are phase controlled converters? Phase means what? Phase means a angle. By varying the firing angle of ACR, we can vary the level of DC output voltage. Okay, by phase control converters, we give fixed AC to get a variable DC, like rectifiers, AC to DC, DC to AC, and all this converting thing is done by our what? A rectifier. So it is a rectifier. Okay, phase control converters are the rectifiers where we give the fixed AC to get a variable DC. And how to get that variable DC? By varying the firing angle of ACR. In ACR, there's a firing angle. We can vary the firing angle. That's how we can get the vary the levels of DC output voltage. Varying DC voltage implies varying the level of DC output. Pretty much, okay. So, yeah, so phase control converters, we can take examples of rectifiers and inverters, speed control DC motor, armature voltage control. Voltage at terminal of DC machine should be applied through a phase control converter. Armature voltage control, voltage at terminal of DC. Okay, classification based on the devices used. Okay, so if you use only diodes, then it is a uncontrolled rectifier. That means you can't control it. Fixed AC to get fixed AC, the controlling part is not in your hand. Then if you are like using only SCR we can vary, we can you control it. Okay, so it is a fully controlled rectifier. So we give a fixed AC to get output as variable DC. So it is varying. So that's why it is called a fully controlled rectifier. There is also semi-controlled rectified or half control rectifier where we use both SCR as well as our diode. Okay, here also you can get a variable DC because it is a same based on the number of pulses. Okay, so one pulse converter. Okay, two pulse converter, three pulse converter, six pulse converter. Okay, so one pulse converter is like one pulse, then zero, then one pulse, then zero, one pulse, then zero. One pulse converter, single phase half wave rectifier. Okay, for single phase half wave rectifier, we pass like one pulse converter, and then two pulse converter. If you want to convert two pulse, it is single phase full wave rectifier, and three pulse, then there would be like three pulse, then three phase half wave rectifier, three phase full wave rectifier. It will be into two, that is six. Okay, so pulse number of times VO repeats, मतलब output voltage repeats itself in one cycle of input voltage. Number of times VO repeats itself in one cycle of input voltage, or we can say number of cycles of VO in one cycle of V in. Like V in is something sinusoidal, but you are getting like one pulse for single phase half wave rectifier VO as like this. Okay, and TO output time period is equals to the input time period divided by the pulse. Output time period is equals to the input time period divided by pulse number. Okay, so frequency would be the inverse, obviously. Yeah, so like this, output frequency. Okay, so output frequency is dependent on like pulse number and the input frequency. Alright. As number of pulses increases, the harmonic content of in V naught or ripple in VO reduces. For higher pulse number, more devices are required, so cost increases. In HVDC, 12 pulse converter is used. Okay, so VO has some desirable part as well as some like the DC part, and the undesirable, that is the like all the harmonics that it have, like fundamental first harmonic, second harmonic, third harmonic, and all this stuff is there. Like the RMS would be V1 square by 2, V2 square by 2, V3 square by 2, root over 1 by 2. Okay, peak to peak ripple is VO max by minus V mean. Okay, pretty simple. Ripple means fluctuation about DC. Pretty simple. If harmonics were absent, then output would be flat. Yeah, we need to remove that. We need to remove the harmonics. That is undesirable part. Got it? Like harmonic analysis. Let's see how the harmonic is done. So analysis of DC output. Okay, something like this. Two pulse, some two pulse. So 2FI harmonic frequency, NF, not 2NFI. Okay, yeah, yep. So all harmonics are even harmonics. Okay, like for two pulse, something like two pulse uh output, so we'll get something like even harmonics and a DC desirable part. Got it. So average RMS value, harmonic wala, like harmonic one, and VORMS would be like this total. Got it. VRF, voltage ripple factor, is harmonic content RMS divided by harmonic by um average or something like that, I think so. Yeah. So harmonic by desirable by, sorry, undesirable by desirable, we can think of that also. If you RMS square minus VO square by 1 by 2. Okay. Hmm. Yeah. Sorry. The form factor. This is a form factor. VRMS by VO. RMS by average. FF score VRF equals to FF score minus 1 root over perfect DC, no harmonics. That means no harmonics should be present, and if there is no harmonics, then we VO only. Yeah, so it would be like a 1, or VRF would be like 0. So yeah, so it approaches 1. But VRMS is always greater than average because it has some, like it is more. It has some this content also, but it has something like this. Okay, so form factor is always greater than equals to 1. Closer the ff goes to 1, the waveform approaches to pure DC. If form factor is close to 1, quality of the DC waveform is high. Okay, so the quality of the DC component would be high. Voltage ripple factor indicates harmonic content in VO as a function of DC output, like the like the like indicates the harmonic content in V naught, like output voltage as a function of DC output. The function of DC output, got it. In analysis of AC harmonics, let's see the analysis of AC harmonics. Okay, voltage of output depends on input voltage, but input current. Okay, so this is the pretty much important stuff we can say. Yeah, so analysis of AC harmonics. So let's analyze. Voltage of output depends on input voltage, but input current depends on load current. Okay, if load current is constant, then source current is either square wave or quasi square wave, so it's non-sinusoidal, hence contains harmonics. Got it. Output of the rectifier contains voltage harmonics, while the input contains current harmonics. So the input contains current harmonics and the output contains the voltage harmonics. How? See, voltage of the output depends on the input voltage. Like the voltage of the output depends on the input voltage, but input current depends on the load current. Voltage of the output depends on input voltage. Output voltage depends on input voltage, but input current depends on load current, like that they are inversely relation. Okay, if load current is constant, if the load current is constant, then source current is either square, source current either square or quasi square wave, so it contains sinusoidal and hence contains harmonics. Okay, so I've understood that the output voltage contains harmonics as well as the input current also have harmonics because it depends on the load or we can say output. That's why the current it tries to make it like DC or like DC, yeah. But for input it should not be, it should it be AC. So it make a square something quasi square. Yeah. So the input current would contain the harmonic contents as like this. Yeah, okay. Like this is the fundamental desirable part. So total RMS. Undesirable part is the stuff. So minus this. Acha. Yeah. Okay, the undesirable part. Similar. G is the distortion factor. Yeah. Like the desirable birthday. ISRMS, total. So summary of AC/DC harmonics. AC side, like the source side, will contain the current harmonics, and the DC side contains the voltage harmonics. DC side has something like form factor we can say, which is like VO RMS but a VO average. So the for like this is the summary. This is what you have to remember, and all the other stuffs should you can just like ignore it or something like that. Okay, and it is only used for single phase half wave rectifier only. We will see that later on in the in the later parts of this chapter. Let's see. So, summary. You want to know summary, yeah? I will tell you. AC side will contain current harmonics and DC side will contain voltage harmonics. Pretty much simple. Now, DC side, yeah, so the DC side has a form factor which is equal to the VO RMS बटे VO average. Okay, the RMS beta average, which is greater than 1. So voltage ripple factor would be root over form factor ka square minus 1. As form factor becomes closer to 1, waveform becomes DC. Like form factor becomes closer to 1, a waveform becomes DC. So obviously form factor will be greater than 1 and it approaches 1. When it is approaches 1, we will get the most desirable waveform that we wanted, and VRF will become like a 0. Voltage ripple factor indicates like the ripple in the DC output. For the AC source side, okay, for the AC source side we'll have the distortion, like the distortion factor, that is called G would be um dono, both are RMS, but IS1 RMS and IS RMS. What is IS1 RMS? IS1 RMS, I think it is the, not thinking, what is IS1 RMS? What is IS1? IS1 was the desirable, okay, desirable by like the total one. Yeah, so it is the desirable by total, and here is RMS by average. Average is the desirable. Okay, and VORMS would be like uh VORMS is the total one. Pretty much that only. Yeah, you can get the form factor, then we can get the voltage ripple factor. Otherwise, if you want me to tell what is the voltage ripple factor, it is the harmonic but the the average one. Getting my point? Like it indicates the harmonic content in VO as a function of DC output, or we can say ripple. Ripple, that means the harmonic. Pretty much simple. That is all. So what I'm telling, I'm not because so we have uh, THD, that is trans total harmonic distortion, which is root over similar 1 by G square minus 1 by G square minus 1. G approaches, G obviously less than 1, and as G approaches, waveform becomes more sinusoidal. Got it? And some more important terms: rectification efficiency. Rectification efficiency is contribution of DC component in total power delivered to load. Okay, like the desirable power, okay, divided by total. Yeah, desirable by total power, we can say that. Na, desirable by total power in percentage into 100, we can say that. And transformer utilization factor, what part of transformer kVA rating is converted to desirable power at load, like the source side. Desirable power is DC power. What part of transformer kVA rating is converted to desirable power at load? Okay, like how much power in the uh, converted to the desirable. So desirable divided by the source power. This was the how much contribution of DC component in total power delivered to load. Like total power delivered to the load, how much is the contribution of the desirable DC component? Here, here desirable power at load to is there, but there is transformer KVA rating, how much is converted? That is important. So we are using something like source here. There was output RMS. So the total, like टोटल में से कितना पावर कन्वर्ट हुआ एज अ डिजायरेबल पार्ट पावर लाइक पावर एंड हियर यहाँ पर ट्रांसफॉर्मर यूटिलाइजेशन फैक्टर में हमें चाहिए डिजायरेबल बट वो ट्रांसफॉर्मर से कितना आ रहा है मतलब सोर्स से कितना आ रहा है वो चाहिए दैट्स व्हाई वी आर यूजिंग समथिंग लाइक दिस ओके या ठीक है पीक इनवर्स वोल्टेज सिंपल inverse is there so we will use the positive number मैक्स और नेगेटिव वोल्टेज अप्लाई बस इन ऑफ स्टेट में कितना कितना वोल्टेज अपेयर कर रहा है अक्रॉस ऑफ डिवाइस या फंडामेंटल रिप्लेसमेंट फैक्टर not important so there is a I think this is a source yeah source voltage and source current no अच्छा desirable power real power got it cos phi अच्छा fundamental got it pretty much that only input power factor on the AC side real power by source yeah अच्छा ओके तो आई थिंक सबको समझ में आ गया होगा और एक बार गो थ्रू कर देते लास्ट टाइम लाइक समरी टाइप सो हम लेट मी टॉक इन हिंदी फॉर हिंदी व्यूअर्स आल्सो कि फेस कंट्रोल कन्वर्टर हमारे पास फिक्स्ड एसी इनपुट लेगा और वेरिएबल डीसी आउटपुट देगा फेस मींस एंगल से कंट्रोल कर किया जाएगा एसीआर में फायरिंग एंगल होता है ना उसको वैरी करा करा के हम डिफरेंट वोल्टेज को वैरी कर सकते हैं डीसी में मतलब आउटपुट में ठीक है रेक्टिफायर इन्वर्टर होता है तो क्लासिफिकेशन में हमारे पास डायोड यूज कर सकते हो एसीआर यूज कर सकते हो दोनों यूज कर सकते हो डिफरेंट डिफरेंट कॉन्फ़िगरेशन है अनकंट्रोल्ड होगा फुली कंट्रोल सेमी कंट्रोल्ड होगा सही है नंबर ऑफ पल्सेस के ऊपर भी डिपेंड कर सकता है सिर्फ एक पल्स हो सिंगल पल्स है ना एक पल्स हो तो सिंगल फेस हाफ वेव रेक्टिफायर का वो होगा टू पल्स हो मतलब आउटपुट ही है ये सब तो ये होगा फुल वेव रेक्टिफायर में ये हमारे पास बनेगा थ्री फेस हो थ्री 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 हो तो थ्री फेसिंग हाफ वेव रेक्टिफायर छः होगा छः पल्स होगा तो थ्री फेस फुल वेव रेक्टिफायर हो जाएगा ठीक है pulse number of times VO repeats itself in one cycle of input voltage or we can say number of cycles of output voltage in one cycle of in like एक साइकिल ऑफ वी इन में कितना साइकिल आउटपुट का आया. दिस इज द सिंपलर वर्ड्स वी कैन से. एक साइकिल इनपुट के कितना साइकिल आया तुम्हारा आउटपुट का, दैट इज व्हाट इट इज. उस पे हमारे पास एक चीज निकला कि एफ ओ इक्वल्स टू पी एफ आई. ओके, आउटपुट का फ्रीक्वेंसी इक्वल्स टू नंबर ऑफ पल्स इनटू एफ आई. ओके, yeah, so number of pulses increases, the harmonic content also reduces. Okay, in VO, or ripple in VO reduces. Okay, the harmonic content of VO is reducing. Number of, like, see, the much you are making pulses, it will become like a straight line. Like, the much it is, the pulse number would be more, it will be straight line. That's why. But it is very harder for you to make that number of pulses increasing. It is very hard, मतलब बनाना बहुत ज़्यादा हार्ड हो जाएगा. क्यों? क्योंकि ज़्यादा नंबर ऑफ डिवाइसेस चाहिए होगा. ठीक है. और हमारे पास HVDC यदि देखोगे तो उसमें 12 कन्वर्टर मैक्सिमम यूज़ किए जाते हैं. तो ऐसा समझ समझ रहे हो. उसके बाद वीओ में देखो ये सारे डिजायरेबल अनडिजायरेबल पार्ट है. मतलब आउटपुट में इनपुट से आउटपुट बनेगा, तो वो डिपेंड करेगा इनपुट का वोल्टेज में. तो इसमें हार्मोनिक कंटेंट आएगा ही आएगा. तो उसको निकालना होगा. तो हम फंडामेंटल, ठीक है, या कुछ भी नहीं है इसमें. तो इससे हमें एनालिसिस करना होगा. किसमें हार्मोनिक एनालिसिस करना पड़ेगा. तो P इक्वल्स 2 यदि सोचोगे तो 2 का हमारे पास क्या होगा कि ऐसा हुआ तो 3 का होगा. ठीक है, 2 का, हाँ ये ऐसा कुछ है. तो 2n समथिंग होगा, 2n एफ आई हार्मोनिक फ्रीक्वेंसी, मतलब इवन नंबर फ्रीक्वेंसीज होगा. तो उसको निकालने के लिए हम आउटपुट में यदि निकालेंगे तो उसमें हमारे पास आएगा फॉर्म फैक्टर एंड वोल्टेज रिपल फैक्टर. प्रीटी मच सिंपल. उसमें फॉर्म फैक्टर के लिए हमारे पास जो फॉर्मूला है वो है डिजायरेबल बाई, नहीं, टोटल बाई वी ओ आर एम एस डिवाइडेड बाई वी एवरेज. वी ओ एवरेज है ना, which is greater than 1, which is approaches to 1. That means we are more, the waveform is more DC, desirable one. Okay, तो समझ रहे हो कि फॉर्म फैक्टर जो निकाला हमने वो टोटल बाई एवरेज होता है, मतलब डिजायरेबल. और ये तो ठीक है, ये फॉर्मूला है, जीरो हो जाएगा. ठीक है, ठीक है, ठीक है. कैसे बना वो भी तुम कर सकते हो. एवरेज निकालो, आरएमएस निकालो, है ना, हार्मोनिक वाला. और इससे हार्मोनिक में क्या करना पड़ेगा, वोल्टेज पर फैक्टर में हार्मोनिक बटे आई थिंक एवरेज वाला आ जाएगा. उसके बाद आई थिंक इसको माइनस करना पड़ेगा, देन ही हमारे पास निकल जाएगा. प्रीटी सिंपल, नॉट उसमें ज़्यादा सोचने का कोई प्रॉब्लम नहीं है. VRF यही इंडिकेट करता है कि कितना हार्मोनिक कंटेंट मतलब है V नॉट में, है ना. वही तो दिख रहा है. VRF में क्या है, VRF में VO हार्मोनिक divided by V average, that is the desirable part. Okay, now, yeah, so golden rule is that output rectifier contains voltage harmonic while current in the input side. Okay, so current का हमारे पास ये कुछ है, desirable part ये है टोटल RMS, मतलब वही सेम सिमिलर टाइप का हमने वही किया, इस हार्मोनिक से माइनस किया, है ना. और उसके बाद डिवाइड कर दिया आई थिंक आर, लाइक द एस फंडामेंटल वन. सो उसमें से ये वाला कौन सा साइड का है, ये AC साइड का है. मतलब हमारे पास जो इनपुट साइड का है. ठीक है, इसमें आता है G डिस्टॉर्शन फैक्टर, जिसका फॉर्मूला आएगा आई थिंक डिजायरेबल बटे लाइक IS1, yeah, IS1 average, IS1 RMS, like the fundamental one, and the total. There was total by desirable, that is average, and RMS. Okay, so that's the difference. Okay, and THF total harmonic distortion, THD, total harmonic distortion would be 1 by G square minus 1. ठीक है, समझ गए। और वो लेस देन वन होगा। यहाँ तक तो सब कुछ समझ में आने लगा है। उसके बाद आता है हमारे पास रेक्टिफिकेशन फ्रीक्वेंसी, रेक्टिफिकेशन एफिशिएंसी। रेक्टिफिकेशन एफिशिएंसी में आएगा हमारे पास एवरेज बाय, मतलब पावर, एवरेज पावर बाय द आउटपुट का एवरेज, आउटपुट बाय आउटपुट का एवरेज बाय आरएमएस, ठीक है, इन 100 कर दोगे तो कितना डीसी कंपोनेंट इन टोटल और डिलीवर टू द लोड, मतलब डीसी के कंपोनेंट में मतलब कितना, मतलब जो वीओ के कितना डीसी का कंपोनेंट है वही रेडिएशन एफिशिएंसी है। ट्रांसफॉर्मर रेडिएशन फैक्टर कितना सोर्स से जा रहा है, या सोर्स से जा रहा है उसमें। ओके, ठीक है। और पीक इनवर्स नेगेटिव वाला कॉस फाई, ठीक है। इनपुट पावर इसमें आएगा पी बाई टीएचडी के आसपास है, बट ये होगा रियल पावर, ठीक है। ठीक है, ये सब क्वेश्चंस कर करके तुमको समझ में ज़्यादा आएगा, ठीक है। लेट्स मूव ऑन टू द नेक्स्ट part, next lecture. Let us see whether we will be completing the single phase half wave rectifier. Yeah, so the single phase half wave rectifiers, wait, let me, let me see whether, Hmm. Hey, so THD के आसपास है बट ये होगा रियल पावर। ठीक है। ठीक है, ये सब क्वेश्चंस कर करके तुमको समझ में आ जाएगा। ठीक है। लेट्स मूव ऑन टू द नेक्स्ट part, next lecture. So yeah, let us see whether we will be completing the single phase half wave rectifier. What? Yeah. In power electronics, due to high power, we majorly discuss inductance, so we use short circuit test. We use a short circuit test because we generally use due to the high power, and the ideal diode is a short. Okay, if I is greater than 0, diode is on, assumption is correct. If I is less than 0, diode is off, like open. Short circuit test. Okay, we just IA greater than 0.